Hello everyone, so today I'm going to talk about a generating function associated with the alternating elements in the positive part of Uq sl2 hat. So let's get started. Okay, so this talk is devoted to finding the multiplicative inverse of a certain generating function associated with some elements in Uq+. This notation Uq+ stands for the positive part of a quantum group Uq sl2 hat. So back in 1995, Rosso introduced an embedding of Uq+ into the Q-shuffle for algebra V with two generators. And in 2018, Terwilliger introduced the alternating PBW basis for Uq+ using Rosso's embedding. And one type of the elements in this alternating PBW basis is denoted by tilde G sub n. And the associated generating function tilde G of t is actually invertible. It has a multiplicative inverse with respect to this Q-shuffle product. And in this talk, we'll give a closed formula for the coefficients of this multiplicative inverse. So first, let's make some conventions. So Z is a set of integers, and F is a field of it's just a field. Sorry, I should delete the characteristic 0. Yeah, it's just a field. All algebras discussed are over the field F. They are associative, and they always have a multiplicative inverse identities. A Q be a non-zero scalar. We just fix Q to be a non-zero scalar in F. That is not a root of unity. And for natural numbers n, we define n sub bracket n sub q to be this q to be n minus q to be minus n divided by q minus q inverse. Okay, so now we give the definition of the algebra Uq+. The algebra Uq+ is defined by two generators A, B, and the so-called Q-zero relations written here. So a squared b minus bracket 3 sub q a squared b a plus bracket 3 sub q a b a squared minus b a q is 0, and we can also swap a and b, and this formula also holds. And this we call the Uq+ the positive part of Uq sl2 hat. Okay, so next we are going to talk about the embedding of Uq+ into a Q-shuffle algebra, which was first introduced by Rosso in 1995. Also, like to mention that there's an alternative description for this B introduced by Green, also in 1995. Basically, the underlying vector space for V is just the free algebra with two generators. We'll talk about this free algebra in the following slide. So we let xy to be non-commuting interdeterminants, and V is a free algebra generated by x and y. So x and y are called vectors. The product of vectors is called a word, and the number of vectors in the word is called the length of a word. The word of length 0 is called trivial, and we denote it by 1. And the collection of all words form a basis for a vector space B, and this basis is called a standard basis. So now we already have a free algebra B. We now I will give a Q-shuffle product structure on V. So here we first look at the example A1, A2 star B1, B2. So the result here will be a linear combination of words. Each word is obtained by shuffling the AIs into the BJs, the A's into the B's, and each coefficient is determined by how the word is obtained. So we might let's see. We can look at the example. So for each time an AI is moved past a BJ, there's a cost of Q to the AI against BJ, where AI against BJ is 2 if AI and BJ are the same, and it's minus 2 if otherwise. So therefore we have the following result: AI A2 star B1 B2. So A1 A2 star B1 B2 is the following. So for example, we can look at this line. We can see that this line is obtained by basically shuffling A2. First shuffling A2 plus B1, and then shuffling A2 plus B2. So the resulting cost will be A2 against B1 and A2 against B2. because A2 is moved past B1 and B2, and similar for the others. So okay, so now we give a formal recursive definition for the Q-shuffle product denoted by star. This description was actually due to Green in 1995. So first, we first discuss how a Q-shuffle product of vectors work. So first, the identity star with anything is still the identity. And for two vectors U and V, U star V is UV plus VU times Q to U against V, where again X against X is and Y against Y is 2, and if X against Y and Y against X is minus. And next, let's look at how a Q-shuffle product of two words look like. So for a vector, first for a vector V, U, and a non-trivial word V, U star V is given as follows, and V star U is given as follows. So we can still see that, for example, in U star V, the result in a resulting linear combination, each word is obtained by shuffling U past some VI, and the corresponding coefficient is exactly generated by how U is shuffled past V1, V2 up to VI. And similar for V star U. And then for for non-trivial words U and V, we also have a following recursive definition of U star V and or U star V. Basically, these two definitions are equivalent, so we can use either one. So next, let's talk about a very powerful result of Q-shuffle algebra. It is actually a Q-shuffle algebra. So the vector space V equipped with a Q-shuffle product star is really an algebra. This was approved by Rosso in 1995. So now we have this Q-shuffle algebra V. We can talk about the embedding of Uq plus into V. So let U be the sub-algebra of a Q-shuffle algebra be generated by X and Y with respect to the star product. So the relations in U are exactly the Q-zero relations. This was discussed by Green in 1995. And so as a result, we know that there is an algebra isomorphism natural sending Uq plus to U, which basically maps A to X and B to Y, in the generators to non-generators. Okay. So now we basically identify Uq plus with the U as a sub-algebra of B. And now we can talk about the alternating words in U. So we basically define G tilde to be a repeating of XY, 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 and G sub n is repeating YX, 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 and W minus n looks like XY, XY, XY starting with X and ending with X, and W plus n, so Wn for n positive looks like YX, 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 Y, so it starts and ends with Y. So these are called the alternating words for the obvious reason. So there's a lemma by Terwilliger in 2018 that says all these alternating words are actually contained in U. Just as a reminder, U is a sub-algebra of V. It's not the entire of V. So this lemma is actually meaningful. Yeah. So now there's a theorem by Terwilliger in 2018 that says the alternating words W minus n, Wn plus 1, and G tilde Gn plus 1 form a PBW basis for U under some appropriate linear ordering. So now actually basically in this paper we are interested in the generative function tilde G sub of T whose coefficients are tilde G sub n. And we are going to discuss the multiplicative inverse of tilde G sub of T with respect to star. We know that this inverse exists because the constant term is y is invertible. Yeah. Okay, so first we define the multiplicative inverse of tilde g of t to be dt. So dt is this inverse, and in our words, we have tilde g of t star d of t is 1, and d of t star tilde g of t is 1. And then we write down this write down this expansion. So basically the coefficients in d of t are written as d sub n. Yeah, so by this formula we have so first by the definition of multiplicative inverse, sorry, we have d0 is 1, and also we have a recursive definition of dn here. So dn is the minus of this summation. Okay, so let's now look at a few examples in dn. So we list out dn for n from 0 to 3. So d0 is 1, d1 is minus xy, and d2 is xy plus bracket 2 sub q squared xyy, and d3 is as follows. We can see that there's actually a pattern in d sub n. We can see that first, each dn is a linear combination of words of length 2n. And also each coefficient in the linear combination is minus 1 times the square. Yeah, so, and also the words appearing in these linear combinations have a certain type set to be Catalan. We now recall what's the definition of a Catalan word. So first we give some weight to x and y. X bar is a weight of x is 1, and the weight of y is minus 1. And the word is a1 up to ak is called Catalan if any partial sum of a weight is non-negative, and also the sum of all the weights of the letters is 0. So the length of a Catalan word is always even, just by definition. And for natural numbers n, we denote the set of all Catalan words of length 2n by cat sub n. So we can now write down, to give an example, we write down what is cat sub n for n from 0 to 3. We have cat also, so cat sub 0 is a trivial word, and the Catalan word of length 1 is only xy. This is the only one. And there are two Catalan words of length 2, of length 4. They will be xy and xsyy. And the Catalan word of length 6, there are 5 of them. And they are exactly those appearing in D substrate in D3. So now, yeah, this observation gives we now have the observation that each dn is contained in the span of Catalan word cat sub n is a span in the span of Catalan words of length 2n, and this is actually true in general. So we have this lemma, and now let's write down the expansion of dn. So for any natural number n and a word in cat sub n, so we have minus 1 to the n of times d of w to be the coefficient of w in dn. So basically we have this sort of the expansion, writing dn as a linear combination of Catalan words of length 2n. Okay, so now we will want to find out what is each dw. So let's now look at the examples. So we list down the Catalan words of length mo6 and corresponding d of w, and we can see that so d of a trivial word is 1, and d of xy is 1, d of xy is also 1, and d of xxyy is bracket 2 sub q squared, and d of Catalan words of length 6 are as follows. And if these coefficients look familiar to you, then that's because they are exactly the coefficients appearing in the linear combination of D3. Yes. So now basically we give our main theorem here. So for any Catalan word of length 2n, we can write down d d of w in enclosed formula here. And moreover, although it's not immediately obvious that this is actually a square, but we recall from previous examples that each d of w is actually a square, and that's true in general. We can write down its square root in two different forms. So now let's talk about how we want to prove this main theorem. We'll actually define some kel d of w as whatever was proposed for d of w. And then in the end, we will show that this kel d of w coincides with d of w. And then the second part, namely each d of w is a square, will just be a byproduct of our proof. So now let's define kel d of w as whatever was proposed for any Catalan word w a1 up to a2n. We define kel d of w as follows. And for convenience, we also define kel d sub x of w as follows. Basically, we capture the parts of, capture whatever was in the product here, but we only want those I such that a sub I is x. And similarly, we define d sub y of w to be a product of whatever corresponds to a sub y is y. And we will show that d of w is actually is both d sub x of w squared and d sub y of w. Okay, so we can now rewrite our main theorem as follows. We only now need to prove these two d notations coincides. They are the same, and also to prove that each d of w is a square, we only need to show that d of kel d of sub x is the same as kel d sub y. Okay, so now let's try to visualize this kel d and kel d sub x and kel d sub y. So recall that, so we now look at this word as an example, xx, yy, xy, y, xy. And recall that the back path for a Catalan word here is basically a path starting from the point 0, 0 to the point, in our case, it's 10, 0, because there are 10 letters in this word. And then basically, each x corresponds to a step working upwards, and each y corresponds to a step working downwards. Okay, so this is our we display our back path as follows, as on the screen, and these blue dots on the first graph basically contribute to d sub x of w. This is by definition. And the red dots on the second graph contribute to d sub y of w. And all these dots will in the end contribute to d of w, kel d of w. So we have a result that kel d of w is a product of kel d of x of w and kel d sub y of w. Now next, we only need to show that this kel d sub x is the same as kel d sub y. And then let's still look at this example. We still look at this back path, and we look at height 2 for an example. So here we call this C level height 1. Sorry, the C level is height 0, and then height 2 is basically this line on the screen. Let's see. On the first graph, we can see that the places where this back path rises to height 2 are basically these two blue dots. And on the second graph, we can see that the places where the back path falls to height 2 are these two red dots. So basically, and since the back path, it starts and ends at the sea level at height 0, so we know that whenever it rises to height 2, it must also fall from height 2 at some point, in pairs. So we know that we can conclude that the number of blue dots at height 2 is the same as the number of red dots at height 2. And this is general for any height. So basically, we can conclude that these two products, d sub x and d sub y, are the same because they are basically multiplying the same sequence of numbers. It's just the sequence is permutated. Yes. So now we have our theorem that for any Catalan word w, kel d sub x is the same as QD sub y. And then we can now write QD of W to be the square of, sorry, this should be QD sub x and QD sub y. Okay, so this now completes the proof of the second part of the main theorem. And now, to prove the first part of the main theorem, let's move on to QD sub n. So now first we define QD sub n in a similar way as we define QD as we define D sub n. It will be the linear combination of Cantor inverse of length 2n with coefficients -1 to the n times QD of W. And we interpret QD sub 0 is 1. And it turns out that through some calculation, this QD sub x satisfies a certain recurrence relation. For n greater than or equal to 1, QD sub n is a minus of Q x star QD sub n minus 1 minus Q inverse QD sub n minus 1 star x. And then we attach a y on the right and divide it by Q minus Q inverse. So now let's move on to our generating function. We define QD of t as if we are defining D of t in the same way. And then using this recurrence relation here, we were able to show that QD of t is indeed the multiplicative inverse of tilde g of t with respect to the Q shuffle product star. So in other words, we have this lemma. Okay, so since we know that the multiplicative inverse is always unique, we now can conclude that QD of t is D of t. And since we basically define QD of t and D of t in the same way, we can conclude that their coefficients are the same. And also, we also write QD sub n and D sub n as linear combinations. So they are linear combinations, so the coefficients in these linear combinations, namely QD of W and D of W are also the same for any Catalan word W. So now our proof for the first part of the main theorem is done. Okay, so the summary is in this talk we first introduced D of t, which is the multiplicative inverse of tilde g of t with respect to star. We then examine a few examples and propose a closed formula for D of W. So next we define QD of W as whatever was proposed for D of W. And using this definition, we were able to find a pretty good recurrence relation for QD sub n. And then using this recurrence relation, finally we were able to show that QD of D is this multiplicative inverse of tilde g of t with respect to star. So in other words, this QD of t is really our D of t, and also the corresponding coefficients are the same. So the QD notation coincides with the D notation, and that completes the proof. Okay, so I guess this is everything in my talk. So thank you for your attention, and I'm open to. I'm happy to hear if you have if anyone are willing to ask any question. Okay, yeah, thanks everyone.